Vector connects the two. V, the vector V connects them, right? Where does vector V start? It's going to start at P and it's going to end at what? Q. And what is that vector? That vector goes what? It's negative I and this is not to scale plus what? 3j. You got that? It says, and this is give 5 decimal places. Okay, so it says give Q the point at a distance of 0.1 in that direction. How do we find P? Well, we know what P is. P is 4, 5. We have to move to Q. How do we figure out what Q is? Can someone give me an idea of how we find Q? Give me one thing I need to do in order to find Q. Yeah, Jerry.
First find the unit vector.
Well, we don't actually need to find, we're not finding a unit vector this time. We're shrinking it to a magnitude of what? A tenth of a unit. We want to go. We know that this distance right here, we'll call this one V1, this vector V1. What's the magnitude of that vector V1? 1/10, right? So we need to go in that direction, but the magnitude needs to be 1/10. How do we figure out what the components are going to be? So V1, vector V1 is going to be 2 components. We know that the magnitude of that vector is 1/10, and we know the direction. How do we figure out what the components are going to be?
4 plus 1 over 10 times the unit.
So how did you, 4 plus, so say that again?
4 plus 1 over 10 times the unit.
What's the magnitude of vector V? What's the magnitude of vector V? No, the square root of what? 10. The magnitude of vector V is 10, but do we want to go that far? No, we want to go how far? 0.1. So we want to go in the same direction, but we want the magnitude to be 1/10 instead. Is everybody with me so far? So how do we figure out what the components are? How do we figure out what the components are for this vector? What do we do?
-1 divided by root 10.
Oh, so -1 divided by what? Root 10 times 1/10.
Yeah.
Exactly. Why times 1/10? You turn it into a unit vector and then shrink it down to, I see why you said unit vector now. So you're taking this, and if you divide it by the square root of 10, it becomes what? A unit vector, but you want it to be 1/10 of that, so V1 is going to be this. So what are those components going to be? So V1, the vector that you want to add to P, the vector you want to add to P is going to be -1 over 10 root 10, comma what?
5 plus
3 over, this is just the vector, someone, not the final point. 3 over 10 root 10. So are you okay with what we just did right now? If not, ask questions right now. So that vector V1 is the displacement from P to Q. The displacement vector. Are you okay so far? Is that vector going in the same direction as V?
Yes.
Yes, but it has a magnitude of? No, what's the magnitude of that? What's the magnitude of V1?
0.1.
1/10, right? 0.1. Okay, so Q is the end of that vector from P. So what's the starting value? So you know Q is going to be what x value? It's going to be 4 plus what? 4 plus -1. I'm just going to write it as plus just so it's consistent. Plus, and then 5 plus what?
3 over
10 root 10. Are you okay so far? So that's Q. You would plug that into your calculator, and the reason they want 5 decimal places is because we're dealing with really small, relatively small decimals, and if you don't go that far, it's going to be hard to be super accurate. Are you okay with A? Okay, so we're going to do a little side journey that you could definitely do without any new knowledge. It says Z is a function of x and y, but x is a function of what? T. And y is a function of t. So if you wanted to find the derivative in terms of t, what could you do? What would you want to do first? Any ideas? Well, what does x equal? Yeah. And what does y equal? So what is z of t in this case? What is z of t? T squared sine of what? 2t plus 1. Now, is that something you could take the derivative of? Yeah, what rule do you use? What's the overall rule? So the derivative of the first times the second plus the first times the derivative of the second times what? Are you okay with that? Now, could I build much more complicated nested function compositions? Could I make z in terms of x, y, and z in terms of a, b, c, d, and a, b, c, d in terms of u and v? I could nest this as much as I want. Are you always going to be able to substitute this nicely? Is substitution always going to work this nicely? No. Are you always going to have this few variables? No. Sometimes you could have something that's almost impossible to substitute, or virtually impossible, or super hard, and or you might have a ton of variables. It's real kind of a pain. So there's another way to go about doing the chain rule when you have function composition of multivariable functions. First, you're going to make a little tree. What's the overall output of this function called? Z. What goes into making Z? X and Y, right? The ingredients, not the function, the ingredients, right? And what goes into making X and Y? T. So the first thing you're going to do is you're going to make this diagram. At the top is your final output variable, and then the next level is what you put in to get that one, and then the next level is what you plug in to get those. Are you okay with this? You connect you label each of those arrows with the partial derivative like this. Partial z, partial y. What do you think goes right here? Partial z, partial x, and then it's partial x, partial t. It's not actually a partial, but it's okay. Partial y, partial t. Make the tree, fill in the tree. Now, if you're looking for dz dt, if you're looking for partial z with respect to t, you draw both paths, or excuse me, all the paths that go from z to t. What's one path that goes from z to t? There's that one, and there's this one. Along the paths, you multiply the partials, and then you add the paths together. So what do you think this is? It's going to be dz dx times what? Partial t plus partial z, partial y, partial t. And now you just calculate those things. You go calculate. So let's look at this. What did we have up here? We had, what was z in terms of x, y? Do you remember? It was, I think it was x sine y, right? And what was x? I think t squared, and what was y? 2t plus 1. I think that's what it was. So what is dz dx going to be? The partial of z with respect to x. What's that going to be? Careful, x is moving. It's just sine y. What's the partial z with respect to y? It's just x. Do you agree with that? You good? Yay? Okay. What's the partial x with respect to t? 2t. And what's the partial x with respect to y? Oh, sorry. Partial x with respect to t. Sorry. Dobichi. Partial x with respect to t. dy dt. I erased the wrong one. Sorry. dy partial t. What is that? 2. Sorry. I was like, what's your plot? That's the easiest one. I am terrible at this. I'll fix it. I fixed it wrong. Ah! Okay. So now you just fill in the blanks. So let's write it out. What's that product going to be? Well, it's going to be sine y. Now it's going to be sine y times what? Dx dt. What's that one? Everybody, so what do we have here? Here's this one. That's this one, which goes right there. Times what? No, dx dt. 2t. Yep.
Plus 2x.
2t. Plus what?
2x.
I think we should use a chain.
Hold on. Just give me 1 sec. Let's just see what happens here. Let's just see what happens here. dz dy is what? X. And then what? 2. Hold on. I understand. I want to see if you can finish this and then fix the mistake at the end. Do you want to fix the mistake now or at the end? Now? Is there a mistake somewhere in there? Where's the mistake? Partial z, partial what? This one right here? Oh, so what's it supposed to be? What's it supposed to be? X cosine y. Good catch. Good catch. Man, good job. Good job. Someone's like, fix it now. Fix it now. Don't let it slide. Okay, so it's sine y times 2t, but then what does it become? Not over here. What is it? X cosine y times what? Good job, Soma. But is that in terms of t right there? We wanted partial z partial t, right? Is that just in terms of t? Is it in terms of t? No. How do we get it in terms of t? Hey, look, everybody, what do we have up here? What does x equal? And what does y equal? 2t plus 1. 2t. Oh, look, what's x? T squared. Cosine of what? Ah, cosine of 2t plus 1 times what? Hey, is that the exact same thing we got before? Let's see. Let's see. How do we do? How do we do? How do we do? Take a look. Is it the same thing? It's written a little differently. So, in this case, does this seem like a little bit more work than what we did originally? Yes. Here's the thing. In some cases, yeah, it's more work. But when we start adding in even more variables that you have to keep track of, you need to keep track of them carefully or it won't work at all. Substitution will not always work. You need to be able to do this in a generalized sense because here's the thing. This tree method, how many input variables could we have for z? As many as you want, exactly. How many input variables could we have for those?
And then you just do the dot product of all of them?
Not the dot product. You just well, you can kind of think of it as the dot product. You do all the trees. You do all the paths. So, for example, over here, what could you have? What does this show us right here? Take a look. What happens here? Z is in terms of what? X. X and Y, right? But X and Y are both in terms of what? U and V. So if I wanted Z prime U, how many paths are there? Those are the yellow ones, right? You multiply this partial times this partial and add this partial times that partial. Same thing over here with for V. This is why you write it out and like write down the arrows. Is it really easy to mess it up? It really is. Let's practice it a little bit. Find the board, everybody.